Okay. So last time we looked at polynomial functions and their graphs. And I just briefly, the way I had worded it before was that now we're going to be using, this desmos.com. I'll go ahead and highlight this as our graphing calculator. Now, because I know that we don't all have a TI-84 or some sort of TI instrument where you have a graphing utility, Desmos.com is going to be your best friend. You're going to need to use this on the homework so that you can make all of your graphs. Make and analyze graphs of functions. I'm going to put f of x to abbreviate functions.
Will that be available for the next test?
Yeah. So the next test is going to be heavy on functions, which means you're going to have to look at and interpret and analyze those graphs. And I'm able to insert this domain so that this will be accessible even though you're using the lockdown browser. Okay, so you will be able to use Desmos. I'm going to set that test up and then try to practice it on my own to make sure that that does work for you guys and you guys aren't locked out of it. Okay. But in any case, we're putting a face to a name. And what I mean by that is that we've been seeing equations, things that look like either f of x or y equals something, right? So we might say that we have y equals x. And this is a very simple function. Its picture, without being too detail oriented here, a rough sketch of this function would just be like a straight line that passes through the origin. Okay. This particular function is a linear function, and we can identify it as a linear function as we identified linear equations because the x has the highest exponent of a 1. Okay. So this is going to be your basic linear function. Sometimes it's called the identity function. And the reason why it's be called the identity function is because your output is identical to whatever the input is. Okay, and if you were to zoom in on this graph and look at, if you were to throw this into Desmos or your graphing calculator, you would see that if you go over to 1 on your x-axis, that is your input, right? That the y value that corresponds to that input would also be at 1. If you went over to 2 on your input axis or your x-axis, then the y value corresponding to that would also be at 2. So the inputs are equal or identical to the outputs, which is why this is sometimes called the identity function. But I think of it as the parent function of all linear functions. This thing can be modified. You could multiply a number times it. You could add a number or subtract a number to it, and it would just have the effect of shifting the graph around or stretching the graph. So there's our linear function or identity function. We briefly talked about quadratic functions. The most basic quadratic function is just going to be y equals x squared. So that's our quadratic function. And a brief sketch of this thing would look something that's U-shaped. Or we call this a parabola, where it passes through the origin, but it sort of looks like an upside down rainbow. This is sometimes called the squaring function. And the reason why it would be called the squaring function is because that's the operation you're doing to the input. The input, whatever the x value is being squared, and then that gives you the output. Okay, so for something like this, if you walked over to 1 on the input and you squared it, well, then you would still get 1 on the output. Similarly, if you were to walk over to -1 as the input, Well, -1 times itself would also be +1. So that's why you get this characteristic U shape. If we were to go over to 2 on the input, well, 2 squared would be 4. So that's why this value up here is pretty high. It would be up here at 4. So as you continue walking outwards, let's say in the positive direction, and your inputs get larger, well, then your outputs will get larger because 3 squared would be 9, 4 squared would be 16. And so you could plot those corresponding x and y values and then get a graph that eventually looks like this. You could also do it with fractions, where like if you put in 1/2 here and squared it, you might want to just take my word for it that if you squared 1/2, you would get 1/4 here. Right? That's why it's sort of like squished between 1 and -1. It looks a little bit low, but once you get past 1, the numbers start getting really large really rapidly. Okay. But the thing here is that we really want to start to say, like, if I see something that's U-shaped like this, I'm thinking that that is the graph of some quadratic. I don't know exactly what kind of quadratic or what other numbers are in play here, but we're going to talk about that in a second. We just want to introduce the face, and we want to be able to put the face to the name. Okay. Another type of polynomial function would be the basic cubic function, y equals x to the 3rd power. And a sketch of that guy would look something like this. Well, this one's actually kind of nice, at least in terms of the naming, this cubic function. You might call the cubing function because what it does is it takes the input value, so 1, and then cube it. So its output value on the y-axis would be a 1 also, since 1 times 1 times 1 would still be 1. But when you go to 2, it should grow more rapidly than the squaring function because 2 times 2 times 2, let's say that that's where the dot is, that would be at 8, right? Similarly, if you were to walk in the negative direction, so this is -1 here as an input, -1 times -1 times -1, the output should be at -1. And you can imagine that at -2, -2 times -2 times -2, that output would be here at -8. So that's why you're getting this sort of characteristic shape for the cubic function. Again, when you see something that's sort of squiggly like this is the way I will always refer to them, squiggly, then you're going to think to yourself, oh, that's got to be the cubic function or the graph of a cubic function. There are a couple of non-polynomial functions that we're going to have to get used to as well. So let me introduce a couple of radical functions or root functions, just so that we can get an idea about what these guys look like. Because I'll be asking you, like, I'll show you a graph and I'll say, okay, what is the parent function for this graph? And you'll have to tell me one of these options. So here's some radical functions. So y equals the square root of x. So the graph of these guys looks something like this. And I'll call this the square root function. And the reason I'm calling it the square root function is because it takes the input x, whatever that value is, and we're just taking the square root of it to get the output. Okay. So if you were to put the input of 1 into the function, well, the square root of 1 is just 1. So this point right here should be at 1, 1. Now, if I put the square root of something like let's say if I went out here to 4, the square root of 4 would be just 2. So that's why this graph seems to be getting flatter as it increases. Because even if we went out to, let's say we went out to 9, well, the square root of 9 would just be 3. So we're up a little bit higher, but not much higher. You'll notice that this function does not seem to be defined for negative input values. So like I don't have any y values over here. There's no graph, no purple line over here for -1. Can anybody think of the reason why I don't have any output values here for -1?
Is it because you can't have a negative in a square root?
Yeah, that's exactly right. So we're going to call all of the functions that we're working with are real defined functions. And what I mean by that is that the outputs must be real numbers. And we know that if you were to take the square root of -1, that you would get the imaginary unit. But since, just for simplicity's sake, the x values that we're using are real numbers and the y values that we're using are real numbers, we would need a third axis. So we would have to have like a 3D chart in order to graph an imaginary number here, because we would need an imaginary axis. And for simplicity's sake, we're just going to worry about this 2D chart. So we're going to say that the square root function is not defined for negative inputs because they produce imaginary numbers. Now, we don't run into that problem with something like the the cube root function. So the cube root of some input. And you'll see that with the cube root function, its parent function's graph looks like this. Something like that. Cube root function. And again, we could think about what the inputs are. So like if I put the input of 1, what should the output be in terms of the y value? Well, if I take my calculator and I take the cube root of 1, well, I get just 1. So this y value has to be 1. But if I take the cube root of some large number like 8, then I get 2 for my output. So this y value here has to just be 2 for the input of 8. And this cube root function, because it's an odd root, it is defined for negative numbers because I can take the cube root of a negative number. So if I put the cube root of -1 into the calculator, for instance, -1, the output will be -1. So the output goes down here, and that's why the graph is going down. There we have our output of -1. And you can imagine if I had a -8 as my input, I'll get -2 on my output, or my y value. And you'll notice that these root functions are very similar to their corresponding polynomial functions. What do I mean by that? I mean that if we were to take a look at the square root function, it sort of looks like a quadratic function that has been tipped over on its side. Like we just rotate it in this direction, and then we covered up half of it, right? Now that sort of looks like the square root function, okay? Similar with our cubic function, if it's going upright like so and squiggling up and to the right, then the cube root function looks like it's just been rotated a bit. Well, it looks like it's been rotated and reflected. But it has this sort of a similar shape, just sort of been rotated or transformed. Okay. So visually they're sort of related to each other. And that's very similar to the actual algebraic operation we're doing here, right? The square operation has some relation to the square root function. And before we talked about those operations being inverses. Well, it turns out that these functions are inverses of each other too. And we'll talk more about what that means later. But the cubic function, its graph is the inverse of this cube root function, right? Because these operations cancel each other out. They are also inverses. Okay. One other function that we're going to look at or sort of be exposed to is the absolute value function. Okay, so we can think of this as just y equals the absolute value of x. And there are other ways to define this function, but I think that this is going to be the easiest way to think about it. Here in the absolute value function, we are taking the input value and then taking its absolute value in order to get our output value. So what you see when you get start throwing inputs into this particular function, if you put the input of 1 in there, or 2 in there, or 3 in there, well, what is the absolute value of 1? It should just be positive 1, right? So I can go over here and say this is positive 1 right there. If I put the input of 2 into the absolute value function, then the absolute value of 2 should just be 2. So I get this point at the location 2, 2. Same thing with 3. The absolute value of 3 is just 3. So I'd be up here at 3. But now if I throw in like 0 as my input, well, the absolute value of 0 is still 0. So I would be at this middle location. The absolute value of some negative numbers like -1 should be +1, right? Because that's the distance from 0. And the absolute value of -2 should be +2. Okay, just going back to absolute value that we introduced at the very beginning of the semester. The absolute value of -3 is +3. So we get something up here. Well, if you look at these dots, it sort of looks like a V shape. So anytime you see a V-shaped function or a V-shaped graph, you should be thinking to yourself, oh, this is an absolute value function. And so we're going to start by looking at transformations of these particular functions. We talked about transformations briefly last time. And we said that the transformations of parent functions, that they follow a set of rules to shift the graph to the left or right, up or down, to stretch the graph, to compress the graph, right? So I said that if you have a function, so like let f of x be a function, that if we have f of x and we add a number or subtract a number, that what this will do is shift the graph up or shift the graph down. Right? And this is essentially saying we're taking the output and adding a number to it. We're taking the output and subtracting a number from it. That will either have the effect of shifting the graph upward or downward. You could also multiply a number times the output. And what that did was, in some sense, it stretched the graph. And we might call that a vertical stretch. And then one other type of transformation that we saw is that if we put a negative number or a negative, multiplied the function by a negative, the output by a negative, then we reflected the graph over the x-axis. So we have 1, 2, 3, 4 rules there. And that is basically we're manipulating the output, right? So remember that f of x here can be thought of as the output. We had some other transformations if we manipulated the input. So if we had, let's say, f, and then the input was adding a number to it, then this ended up shifting the graph to the left, which seems a little bit counterintuitive. But if we subtract some number from the input, then we're going to shift the graph to the right. If we took the input and multiplied it by a number, so a times the input, then this is going to be a horizontal stretch. And then if we took the input and made it negative, then that would be a reflection over the y-axis. Okay, and I know that was a lot of writing, so I'll give you guys a chance to catch up and ask any questions if you have any. And I guess for clarification, here is like x is the input, so remember that. Okay. So let's take a look at some transformations. Okay. So given the parent function let's say y equals x squared. Okay. So this parent function, we should sort of think once we see x squared that its graph originally looks like some sort of parabola or U-shaped object. Okay. We need to relate the following functions to this parent function. Okay. So we're just going to verbally describe these things. If I had f of x is equal to x squared plus 10, then verbally, how would you describe how this function compares to the graph of this function using those rules that we just introduced?
It's going to shift the graph
Yeah.
to the left by 10 spots.
Oh, but be careful here, right? So our output is being manipulated. So y is equal to x squared. So you can think of this x squared as being the output. And compared to the original parent function, we're adding 10 to the output. So this should shift our graph of our parent function up 10 units. So we could think about having a sketch of this graph here, and we would go up. I'm just going to put a little dash there and say that, pretend that that's 10. That is where our new function would begin. This reference point in the very middle of that function will be shifted in the upward direction 10 units. So it'll be up there. And right now it sort of feels like you're just taking my word for it, right? You could, in essence, come up with a table of the original parent function. So we could say these are input x values, these are y values for the original parent function, x squared. Okay. And then I'm going to have another column in my table that says, okay, y is equal to x squared plus 10. What happens when I add 10 to the output values, right? So we might want to fill out this table by just coming up with some input values to plug into the function, like -2, -1, 0, 2, and 1. Sorry, I probably should have counted in order 1 and 2. There we go. We can plug these into the calculator or calculate what is -2 squared. We should get 4. -1 squared is going to be +1. 0 squared is 0. 1 squared is 1. And 2 squared is 4, right? So that's the original parent function, the coordinates or the points that we could plot for the original parent function. 1 and 1. 2 and 4. If we wanted to be super accurate, right, with the location of these points. The same thing for 0, 0 would be here. -1 and 1 would be like this. And we see that this graph is sort of symmetric on the negative and positive side. So there we go. You would get these points, and then you could draw the curve through those points. Okay. But what happens if we take the output and then add 10 to it, right? This is like using order of operations. You could plug this input into this function here and say, okay, -2 times itself is 4 plus 10. Or you could just take the original parent function and add 10 to the output. So in any case, you'll get 14. We're just going to add 10 to this. We should get 11. We should get 10 here. We should get 11 here. We should get 14 there. But you notice that all of these y values now are all 10 units higher than the original function. And so that's why adding 10 to the output has this effect of shifting the graph up. So like if I put 1 here and squared it, I would get 1. But then I add 10 to it, so I would really be going up here to 11. If I had 2 here and squared it, I would get 4. And then if I added 10 to it, I would be up here somewhere, and we would call that 14. Okay, but you don't want to go through the process of like coming up with this table for every particular graph, which is why I've given you these rules so that we can just say, okay, if we trust that these are true, and we could test them out ourselves if we really wanted to. But if we trust that these are true in general, then we don't have to go through the process of making a table every time we want to graph something, because we just want like a rough sketch. So let's do another transformation, right? Let's take our parent function, which was x squared, and this time we'll subtract 5. What does this operation do to the graph of the parent function?
So shift it down?
Yeah. Yeah, so you're just going to flip back and reference those rules until you get used to thinking about what the rules do to the graph. So this is going to shift the graph down 5 units. And that makes sense because we would take the input, square it, which would sort of be the output of the parent function, and then you're taking away 5, which is lowering the y values by 5. Okay, so in general, we could just say, okay, I'm not going to worry myself too much about calculating these values. I know that the whole graph is going to be shifted down 5 units. So let me just say that the vertex will be down here at 5, and then it will retain its usual shape. All of the points got shifted down 5 units. So that's my brief sketch. Didn't have to do really hardly any math there. Just thinking about what this operation does to the graph of the parent function. Does that make a little bit more sense? Okay, let's think about multiplying this function by something. So we could have this function, and then let's say we had 3 times x squared minus 5. So 2 things are happening to this parent function, right? You can think of the x squared part as being the parent function part, but we've multiplied the output by something, and we've subtracted something. So there's 2 things that are happening to this graph. And we don't have to think too hard about it because we've been given a list of those rules to see what's going to happen to the graph. So we're just going to say, okay, okay, self, I've multiplied by a 3, and according to the rules that Mr. Aguilar has given us, that's telling me that I am vertically stretching by a factor of 3, whatever that means. And I've subtracted 5. So I'm going to shift the graph rather. The graph down 5 units. But just for demonstration purposes, we've described this verbally, so I could draw this graph now and say roughly it's going to be down 5 units, so the vertex will be down here. But because I've stretched this by a factor of 3, you would see that this thing is a little bit skinnier, like so. And again, right now, it just feels like you're just supposed to be taking my word for this. So let me demonstrate why this is going to be true. Okay, so remember, we're thinking about 3 continued. We're thinking about y is equal to x squared, and we're thinking about y is equal to 3x squared plus, minus 5 simultaneously. So let's just put them both into a table where we have some input values. The first graph is y equals x squared. I'll just use the same values as before. -2, -1, 0, 1, and 2. And we already have the output values for these. It should be 4, 1, 0, 1, and 4. Pretty symmetric, about 0. Now y is equal to 3x squared minus 5, and we'll see how this compares to the parent function. Okay, so my parent function, its graph looks something like this. 1 and 1, 2 and 4. That's fine. -1. So we have boom, 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 boom. Yeah, something like this. We're going to curve this up a bit. Boom. Not perfect, not particularly pretty either. This is not an art class, so these things don't have to be pretty. They just have to be sort of roughly accurate. And then once we get the output values for our transformed function, we'll look at and compare how the graphs look compared to each other. Okay. So here I'm just going to throw -2 into this equation and get the output. So -2 times itself would be 4, but then I'm multiplying it by 3, so that would be we could just throw it all in at once, actually. So 3 times -2 squared minus 5, right? To get that output equals 7. So we get 7 there. And then we can just keep copying and pasting and just replacing the input value. So 1, -1, gives us the output of -2. 0 would be -5 here. Oop. +1 gives you an output of -2. So it looks like this thing is symmetric as well. We can guess that this one's going to be at 7, but let's go ahead and double check that. 4 squared would be 16, times 3 would be something, and then minus 5. Oh, I'm sorry. I'm supposed to be using the input value. So my bad. That'll be 2, which gives us 7. So 2 squared is 4, times 3 is 12, minus 5 is 7. That makes sense. And we do retain that symmetry. It looks like -5 is the lowest value. Then we go to -2, then 7. So we're going up in both the negative and the positive direction. So we can plot these x and y values as ordered pairs. So -2 is out here. Let me start at 0, actually. 0 and -5. 1, 2, 3, 4, 5. There's my -5. And then we have -1. And then we're down here at -2, so like that. 0 and -5, we already had that one. -2, +7, so 1, 2, 3, 4, 5, 6, 7. And then we have 1 and -2. So 1 and -2 is down here. 2 and +7 would be up here. So we can see if we draw our curve through these points that it's lower, but also sort of skinnier. But again, you don't want to go through the whole rigmarole of plugging these things in and then just getting a like a very accurate graph. For this particular section in the homework, you just want to be able to say, okay, this is the parent function. This is what generally is going to happen to the graph. We're going to shift down 5 units and then are stretched by a factor of 3, so it should get skinnier, sort of like stretching a rubber band. Okay. Some other transformations. F of x is equal to negative x minus 5 squared plus 4. Okay, so all I need you to do here is look at the equation as it's given and think about or verbally describe what are the transformations that are going to be done to the parent function so that we can generate a sketch of this graph. So just look at the rule sheet and tell me what transformations are being applied here.
It's going to reflect the graph over the x-axis.
Yes.
And also it's going to be a vertical stretch and shift graph up 4 units.
Well, it's not going to be a vertical stretch.
No.
But you're right that we have a negative value here. It looks like we took the input and subtracted 5. And then we took the output, this thing that was squared, and then we added 4 to it. So what I do is I literally highlight the things that have been changed compared to the parent function. I say, okay, based on the rules tell me that if I throw a negative here into the function, that's a reflection over the x-axis. So you're absolutely right about that. We're not multiplying anything by the input or output. So like there's not a number here being multiplied by the x. But we are subtracting a number from the input, the x value. So if we're subtracting a number, that says that we're going to shift to the right 5 units. And then this one is saying, okay, we're shifting up 4 units. Does that make sense? So if I asked you to sketch the graph, recognizing that the parent function looks something like this, because we're still dealing with a quadratic function, so the parent function looks like that, then our transformation will look something like we shifted to the right 5 units, so 1, 2, 3, 4, 5. We're shifting up 4 units, so 1, 2, 3, 4. So right here at 5, 4 is going to be the vertex or the reference point for this. But if we're shifting over the x-axis, that means we're going to be flipping this guy upside down. So we can just say, start at this point and then draw a parabola that's upside down. That is good enough for government work. That's what our graph is going to look like. We're not worrying about where the exact points fall. We just want the general shape of this graph. Okay, so think about this now. Think about the following graph. One, two, three. 1, 2. This is 3. This is 2. There's our reference point. Okay, think about this graph. What is the equation for this graph? And if you need these points, this is at 2, 3, 4. This point is at 3, 2. I think that's the only one we really need, 3, 2. You're going to be given problems in the homework that give you a graph and say, find the equation for the graph. And what you need to be able to do is ask yourself, what transformations have been applied to the parent function in order to shift it to this location? Okay. So what you need to do is look at the graph and say, based on this single reference point, how has the graph been shifted? Has the graph been flipped upside down? And so what I would do is list out the transformations that have been applied to the original parent function. So for this, we can say that the original parent function, because it has this U shape, the parent has to be f of x or y is equal to x squared. The basic square function or the quadratic function. Okay, but because the parent function starts here at the origin in the middle of the coordinate plane, we've actually shifted over to the right 3 and then up 2. So if we list those transformations, we shift to the left 3. Sorry, we shifted to the right 3, my other left. And then we shifted up 2. Then that tells me that my function should be y is equal to, if I shift to the right 3, then I should have in parentheses x minus 3 squared. Because that is the transformation that if we subtracted 3 from the input, we would shift to the right. And we want to move this guy over to the right 3 to get to this point. But then we also want to shift up 2 to get to this point. So we're going to add 2 to the outside. So if we can list these transformations that we know visually have been applied to the graph of the parent function, then we can start to interpret or infer that this has to be the equation that goes with this graph. Okay, so let me give you another one that's like that. Write the equation for the graph so here's my graph. 1, 2, 3. That's going to be -3. 1, 2, 3, 4. That's going to be +4. I'm going to say that my vertex is right there. And I'm going to draw this upside down. Okay. So you might want to run through a checklist, right? First, what is the parent function? So what is the parent function that generates a graph like this?
The
F of
square.
x equals x squared.
Yeah. Yeah, f of x equals x squared, or you could just say y equals x squared. Because remember that f of x is the same thing as y. Okay, so that's our parent function. The next thing you're going to ask yourself is to list the transformations. And transformations in broad sense is just saying like, okay, has this graph been shifted somewhere? Where has it been shifted to? Has it been shifted to the left or right? Has it been shifted up or down? And then just list those transformations as a verbal description. So compared to the parent function, which we know starts right at the origin, at this point here, where did we shift this middle point to?
Left,
We shifted it to the left how many units?
-3.
Yeah. Well, we'll just say left 3 units because the left implies the negative direction. Okay. And then we also shifted up 4 units, right? And then in general, the general form of an equation like this is something that looks kind of complicated. I'm just going to put f of x is equal to, and then I'm going to put something squared, and I'll put my input here. But general form looks like this, minus, I'm going to put a value here. I'm just going to call this a. I'm going to call this h, and I'm going to call this k. A, H, and K. You could think about these as being the parameters that affect the transformation, where the number out here influences the vertical stretching. The number next to the input is the horizontal shift. And then the number on the outside of the parentheses is the vertical shift. So we're going to use this general form in conjunction with the list of the transformations that we've come up with, and just throw these numbers into this formula to get the general form for this particular equation. So we would say that this particular equation, let's just for now say that we haven't done any vertical stretching. So I'm going to leave the a, it's at default, this is at 1 because multiplying by 1 does not affect the rest of the function. But we said that we shifted to the left 3 units, and based on the rules that I just gave you, then we must have x to the left means that we're adding 3 inside the parentheses. Let's see. Yeah, and remember, to the left means that we're adding a number to the input. Shifting up 4 units means that we're adding a number to the outside or to the output. So this is the equation for our graph. Oh, you know what? I forgot another thing. This thing is upside down also. So flip upside down. So if it's flipped upside down, then we need a negative in front of the function. So maybe I'll put a little arrow here and say a negative sign flips the graph upside down. Okay. So now I want to look at some examples of the square root function doing the same kinds of problems. Okay. So given the square root function, y equals the square root of x, and its graph starts at 0, 0, and then sort of looks like this. I'm going to say, 1, we need to describe the transformation. And then 2, I want a sketch the graph of the transformed function. Okay, so I wish I had numbered with numbers there. We'll start with Roman numerals, I guess. If I have the function that's the square root of x minus 7 on the outside, write a verbal description for what that is, and then draw a sketch of what that graph looks like. If I gave you f of x is equal to 2 times the square root of x plus 3 on the outside, verbal description, sketch of the graph. F of x is equal to negative square root of x plus 2. Now I'm going to say minus 3 on the outside, and then sketch that graph. Okay, so for each of these 3 options, write a verbal description of the transformation that's been applied, and then draw a sketch. I'm going to give you guys about 5 to 7 minutes to work on this. And remember, we're relating it to the square root function, so the graphs should look like this shape, not a parabola or U-shaped graph. But the same rules will apply. Does anybody have any questions?
Yes,
Okay.
but when we check all of them.
Yeah, maybe.
Yeah.
So
It's more like the reflection. I get so confused in the reflection.
okay, yeah, for sure. You know, just before I jump into these problems, I can maybe give you a way of thinking about the reflection rules that might help clarify. It might not. It's just the way that I think about them. I'm trying to find the page with all the rules on it. Okay, there it is. All right. So the way I think about these reflection rules, these last ones here are, is the negative sign on the outside of the parentheses, or is it inside the parentheses? And so that's how I sort of differentiate these things. Like even when, you know, I introduce this as the output is being, there's a number being added to the output. Well, in my head, I really say to myself, if there's a number being added on the outside of the parentheses, then I'm going to go up. If there's a number subtracted on the outside of the parentheses, I'll go down. If there's a number multiplied on the outside of the parentheses, then it's going to be a vertical stretch. And then that's how I differentiate that from shifting left or right, or horizontal stretch, or reflection on the y-axis. So like, this example here that we did, I would say to myself, okay, the negative sign's on the outside of the parentheses here. So that's what's telling me that it's an X reflection. I'm subtracting a number inside the parentheses. So that's left and right. So just have to remember that subtracting means go to the right in that case. And that one's counterintuitive because you sort of want to think that the adding a number will push it to the right in the positive direction. But in that case, in this particular case, you don't get that situation. So you just have to sort of remind yourself that when you're inside the parentheses, the opposite thing is happening of what you expect. On the outside of the parentheses, the exact thing is happening that you expect. And when you add 4, you go up 4. Okay. Okay, so let's jump into the problems that we were just given and think about it in terms of adding something outside the parentheses or outside the parent function, okay, or subtracting, right? So if I'm subtracting 7 and I'm on the outside of the parent function, I don't have parentheses here, right? But I can think of it as like I'm outside of the parentheses or outside the parent function. If I'm subtracting 7, then exactly what I expect to happen will happen. We're going to shift the graph down 7 units, right? So I'll verbally just say that this is going to be down 7 units. So I'll start my graph here. Since that's the only transformation, I'll just go 1, 2, 3, 4, 5, 6, 7, right? And it doesn't have to be perfect. I could have just done a single tick mark and then labeled it 7. But since that's the only thing that's happening to our graph, or the only transformation that's been applied, then we should roughly have the exact same shape going the exact same direction. Because nothing else was changed. We weren't flipped, we weren't stretched, we just shifted this original parent function and the reference point, which is this little reference point. We just shifted that down 7 units. Okay. Don't overthink that. Again, just a single transformation, shift it down 7 units. Okay. For the second graph, it looks like 2 transformations have been applied. And so I might label those transformations. I might say, okay, I'm multiplying a number by the function. So that's telling me something. And then I'm adding a number on the outside of the function. So if I'm multiplying a number, that has to be a vertical stretch. So the parent function is going to get a little bit taller and a little bit skinnier. It's sort of hard to think about with this function, since what does it sort of mean to be skinnier? So we're just going to make it, when we stretch it like a rubber band, we're We're going to stretch it vertically, and it should get skinnier, right? And then this thing is saying, if we add 3 to the outside of the function, we're going to shift up 3 units. So I'll start with that shifting upward 3 units, 1, 2, 3. And the reference point will stay in the same location. But now I just need to make my graph a little bit taller and skinnier, like so. If you wanted the exact points for these for this graph, then you would have to plug in input values, so like 1, 2, 3 into the function, get the output values to see where the y values fall. But I'm not really concerned about that. I'm really just concerned of, can you label what transformations have been applied, and generally can you describe what the graph will look like? Okay, was there any questions on that second one? Okay, for the third one, we are looking at the third one. It looks like a couple of transformations being, or a few transformations are applied. I have a negative sign on the outside of the function. I'm adding 2 on the inside of the function. And I'm subtracting 3 on the outside. So based on the rules, if I have a negative on the outside of the function, or the outside of the parentheses, or on the outside of the square root, whatever it is, this should be flipped across the x-axis. And there's a number of ways to describe this, right? I think the easiest way to think about it is think about flipping it upside down. Because if this right here is the x-axis, and the original parent function sort of looked like that, then if we multiply that by a negative, it should be flipping across here. So you'll get sort of an upside down arc shape. But in any case, we'll get to that in a second. We really want to move the reference point first. And so this indicates that we are going to move to the left 2 units, but also down 3 units. Excuse me. Okay, so we want to move the reference point to the left 2 units, so 1, 2. There's negative 2. And then down 3 units, so 1, 2, 3. So that's negative 3 since we went down. So there's my reference point. And we just flipped the parent function across the x-axis. So now we should be sort of shooting this arrow in this direction. It's upside down now.
I have a question.
Yeah.
You know, when you put a negative as the reference that you give us, it will be not reflected the x-axis. Is the same like flip it across the x-axis?
Yeah. Reflected or flipped across the x-axis are 2 ways of describing the same transformation.
Okay. Thank
So
you.
whichever one is easier for you to think about. Because if we think about a reflection, right? When you look in the mirror, imagine that the x-axis is a mirror, right? And if this graph was looking in the mirror and it was reflected across that mirror, it would look something like this. And that's the same idea as saying, okay, I could just take this function, flip it upside down, and it would fall in the same location. So whichever way is easiest to think about. That's what I mean when I say reflected across the x-axis. I mean flipped across the x-axis.
Okay, thank you.
Yeah. Any other questions? Yeah, and this is the language when we're talking about math and functions, and the formal language of it is the words always sound very similar to words that we use in everyday life, but mathematicians mean something very specific. when they say certain words, and then they have a lot of synonyms or slang for talking about things. So be sure to ask any questions. If I say something that doesn't make any sense to you, or maybe it's a little bit fuzzy, you can always ask for clarification. I'm definitely down to clarify things. Let's think about this next graph. So 4, since I'm going to keep up my Roman numerals. F of x is equal to the square root negative x minus 1 plus 2. Okay. So think about that for a minute and draw a sketch of what you think that this graph will look like. Okay. What are the transformations that have been applied to the parent function here?
It reflects over the y-axis.
Yeah, reflect over or across the y-axis. What else?
Shifts to the right 1 unit.
Shift to the right 1 unit.
And then move the graph up 2 units.
Up 2 units. Cool. So we could think about this. I always think about it in terms of, okay, here's our parent function, blah, blah, blah. It starts at the origin and then sort of shoots off like an arrow in this direction. But this is the parent function, which is y equals the square root of x. The transformation, if we just follow these rules, right, we're shifting up 1 unit. I'm sorry, shifting to the right 1 unit. Shifting up 2 units, so 1, 2. So right here is our reference point. And then reflecting across the y-axis. Well, This is the y-axis right here. So if I were to reflect across the y-axis, I wouldn't be going upside down anymore. I would be flipping this direction. So using this point, I should say the graph should go in this direction. Yeah. Does that make sense? I mean, does it make sense in the context of the rules that I've introduced so far? Maybe it doesn't make a whole lot of sense in terms of like real life applicability. Okay. Let's do this. So when we talk about graphs, we're going to be talking about symmetry just briefly. And the idea of symmetry in mathematics is very similar to, I mean, the way you think about symmetry, I guess to begin with, you probably learned about symmetry in like an elementary school math class, right? Where like you could write, draw a shape like a triangle. And then you could say, is it symmetric across this line? Or is it symmetric across this line? Or is the shape symmetric across this line, right? And some shapes have some symmetry across different axes or axes. Axes is plural for axis, right? So this idea of symmetry, we're going to think of, can I flip or fold the graph over on itself and end up with the same shape? Or in other words, does it fold over perfectly onto itself? In the same way that if I were to fold this triangle across this axis right here, this diagonal axis that I've drawn, if I folded this part over to this side, well, it should fold perfectly onto itself. Sort of hard to think about it. But you could think about it like a sheet of paper, right? Like this sheet of notes that I have. Imagine an imaginary axis right here in the middle of the page. I would say that, oh, if I fold this over on itself, it's symmetric in shape. If I were to fold it across some sort of diagonal axis, because it's a rectangle, it is not symmetric because it doesn't fold over perfectly on itself. If it were a square, it would be. Right? So that's sort of the idea here. Let's look at some graphs and determine, you know, are they symmetric across the x-axis, across the y-axis, and then we'll talk about symmetry across the origin and what that means. So I'm going to draw a sketch of a graph, and then we'll just ask ourselves, is it symmetric about the x-axis? So symmetry. Here's my graph. Well, here's my graph. And excuse the, you know, I'm not an artist. This isn't a perfect shape, but if I asked you, is this symmetric about the x-axis? Or across the x-axis? Like if I were to fold this graph, this top part, over onto itself, would it fold perfectly onto the bottom part of the graph?
No.
Yeah, so this is no. But what about if I folded this graph in half across the y-axis?
Yes.
Yeah. And then if I can do both, if I can fold it across the x-axis and then across the y-axis, which is harder to think about, we would call that symmetric about the origin. So let's sort of think about this origami that's literally about to unfold, right? If I folded this portion across the x-axis, I would originally have these two downward portions, right? But I'm folding the top over the x-axis. So then I would get something that looks like this. I think. And then if I folded it over again across the y-axis, so this is a reflection, or really a folding over the x-axis. You know what? I'm pretty sure that the reflection across the origin is a diagonal reflection. So it's not necessarily both of these. So this would be like folding across a diagonal axis. So something that looks like this. If I fold this graph across the diagonal, would it be symmetric?
No.
And in this case, it would be no. Okay. Okay, let's look at another example. This is a graph. It's not necessarily a function, but it is a graph. Let's say there, 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 and there. And let's pretend that my ability to draw perfect circles is great. Is this thing symmetric about the x-axis? If you folded it over the x-axis, would it fall perfectly in
Yes.
line with itself? Yeah. What about the y-axis? Let's pretend that this is a perfect circle.
Yes.
Yeah. If I folded it across some perfectly diagonal axis, would it fold over on itself?
Yes.
Yeah.
Yeah. So this one has all three symmetries. Okay. Let's do a third example of a graph. Okay. Is this symmetric across the x-axis? That is, if you folded it across the x-axis, would it?
Yes.
Yeah. Yeah. What about the y-axis? If you folded it across the y-axis, would it fall perfectly onto itself?
No.
No. And that's because there's not any graph over here. So if you folded it across the y-axis, it would fall onto nothing. Okay. What about the origin? Remember, symmetry across the origin is symmetry across this diagonal. So if I were to flip this across the diagonal, it wouldn't fall onto anything. So it's not symmetric across the origin. Okay. So that's when you have a question like that in MyLabs Plus, if it comes up, then that's what you're going to do in your mind. You're going to imagine folding that piece of paper over to see if that symmetry exists. Okay. And I think that we could leave it at that. So let's go ahead and take a 10-minute break. Let's come back at 1:55 and we'll get onto some new material. And if you're given this operation, f plus g of x, what you're actually literally going to do is take the output value of function f and add it to the output value of function g. Right now, this is going to look like weird notation, and it sort of looks like the distributor property, but when we're talking about functions, that is not what's going on. A lot of times in math, the notation that we use is context dependent. So here, remember that the parentheses is not indicating multiplication. It's just indicating the input for the function. Okay. In any case, what this is telling you to do is just to add the output values of the two functions. So add the outputs. That is, add their y values for some x value, right? So this guy is the input value. So if I were asked, if I asked you to take the function f and g at some value of x, let's say 2. Well, then what I would have to do is look at the graph or look at the equation for both of these functions simultaneously, plug in the value of 2, whatever the input that's given is, get the output value for the first function, get the output value for the second function, and then just add those numbers together. Okay. Subtraction is really similar and is written in a similar fashion. F minus g of x is just saying take the output of f of x and subtract g of x. But what I like to do when I write this is I tend to put parentheses around here just so that we're careful. Because if this is a negative output value, make sure you're distributing that negative times the negative. So you'll have to watch out for that specific case. We also we can multiply functions. And that's written as fg. Just right next to each other. We don't even put the dot in between them. Fg of x is implying that you're going to take whatever the output value of x is, and you're going to multiply that by whatever the output of g of x is. And then finally, we have division. And division is fairly straightforward. Whatever the function value for f is, we're just going to divide it by whatever the function value for g is. And so you're literally just going to write whatever the output is for the f function, the first function, over the output for the second function. If that's a fraction that can be reduced, then you reduce that fraction. But if it can't be reduced, then you just leave it as it is. Another thing that you'll have to watch out for is that sometimes g of x might be 0. And so we don't want g of x to be 0 in this case because we can't divide by 0. Okay. So those are the 4 typical function operations that we will look at. And I'm going to jump right into some examples so that we can sort of get squared away on this and it won't be too intimidating for too long. Okay. Okay, so let's look at some example problems. You might be asked to find f minus g of 1 when f of x is equal to 3x squared plus 3 and g of x is equal to x plus 6. Okay, so I'm going to box in the 2 separate functions that they've given us. They've given us f of x is equal to this guy, and they've given us that g of x is equal to this equation. In this case, in this problem, the functions were given as equations. Okay. So can anybody tell me what the input value that they've given us is?
1.
1. Okay. So we'll identify that 1 is the input value. And if we remember what our rule, which I just gave to you, right? So it might be hard to remember. You might need to flip back. The rule for addition is that if you're subtracting the two functions at this one input, then what you're really doing is going to find the output of f evaluated at 1, and then whatever that is, you're going to subtract from it whatever g evaluated at 1 is. Okay. So that means we're going to plug the number 1, since that's the input, into this first function. Okay, so if I plug the number 1 in here into this function, what should I get as my output?
Six.
Yeah, 6. Is anybody unsure of how I got 6?
I am.
Okay, so what this is telling you to do is evaluate the function f when you're given the input or the x value of 1. So in order to do that, I would have to say, okay, let me take 1 and say f of 1 is equal to 3 times 1 squared plus 3. So if I use my order of operations or just use the calculator here, 1 squared is 1, times 3 is going to be 3, plus the other 3 is going to be 6. So that's my output. So f evaluated at 1 is 6. Did that clarify anything, Kelly?
Yes, it was just because it wasn't written down that
Yeah.
so I just made it a third step.
Okay, yeah, for sure. And then we're going to subtract whatever the output is when we evaluate the function g at the same input value. So I'm going to plug 1 into this function, which would effectively be g of 1 is equal to 1 plus 6. So 1 plus 6 should be 7, right? So this is the output when we plug the input into g. So 7 is the value that we get here. So I've just taken this input value and plugged it into this function, the second function. And so this operation that I was trying to do, f minus g evaluated at 1, says to take the outputs of each of the function given this input and then subtract them. So 6 minus 7 is just -1. And that would be my final answer. So let's use the same function and the same set of functions, and let's find f plus g evaluated at 3. These same two functions, though, are going to be f and g. So you could do this in a number of different ways. I like to say that what we're going to do is take f evaluated at 3 and add that to g evaluated at 3. And then what you might want to do is some scratch work over here to the side where you actually plug in the 3 into both of the functions. So f of 3 is, well, let's go back up to the top where we wrote that function. So it's 3 times 3 squared plus 3, which is 30, I believe. And then g of 3 is equal to 3 plus 6, which is equal to 9. So those are the two output values that I'm working with. Were you guys able to get 30 and 9? Or did I make a mistake?
Yes.
Okay. And so this problem is just saying take the output values when you evaluate the functions at the value 3 and then add them. So what we're really doing is just taking 30 plus 9, which is 39. Does anybody have any questions about this problem or this set of problems? Questions, comments, or concerns? I want to clarify any sort of confusion. Does this seem okay? Okay, let's do some more. This is really 3. Find f plus g evaluated at -1 when now our functions are changing. F of x is equal to x plus 3. And I'm going to put g of x is equal to x plus 6. So again, I like to write this out as f plus g of -1 is really saying find f evaluated at -1. And then I'm going to add that to g also evaluated at -1. So the scratch work I'm going to have to do is plug -1 into each of these functions. So f of -1 is going to be -1 plus 3, and g of -1 is equal to -1 plus 6. We can simplify these, and we should get 2, and we should get 7, right? Sorry, that's not right. I went the wrong direction. 5.
5.
Yeah, there we go. And then we're just adding those values together. So f of -1 we found is just 2. G of -1 is 5. And we're adding those together. So this thing that they're asking us to find is just 7. Using these same functions, I want you to find f times g of 0 and f divided by g evaluated at 0. So take a few minutes to think about that, use the rules, and see what you come up with. Does anybody have a possible answer for this first one, f times g evaluated at 0?
18.
Yeah, it's 18. So this is just telling you to take f evaluated at 0 and multiply it times g evaluated at 0. And when you plug 0 into these two functions, 0 plus 3 is just 3. And then 0 plus 6 is just 6. So we should just get 18 for this one. And what about the second one? Well, we should be getting f evaluated at 0 over g evaluated at 0. So I just heard somebody say something.
Is it 0?
Well, let's take a look, right? What is f evaluated at 0? What is the output that we get? If I
3
plug,
divided by 6.
3.
yeah, it's 3. And then if I get g evaluated at 0, I plug 0 in here, and what do I get?
6.
So 3 over 6 is the fraction that I end up getting when I divide these functions. Okay. But I have to reduce this fraction, and I can reduce it to 1/2. So that should be the answer there. So just because you have the function evaluated at 0, again, this is not multiplication by 0. This is saying take the function and plug 0 into whatever the equation is, get the y value. Take 0, plug it into the other function, get its y value, and then divide those outputs. If it's a fraction, we'll reduce the fraction.
Okay, that's what I did.
Yeah, so again, the notation is a little bit tricky because I think that when students see parentheses, they want to multiply. And when we're talking about functions, the parentheses don't necessarily mean the same thing. Right? Like when I wrote f of x, this is not f times x. This is you take this input, plug it into whatever the equation is, and then give some output, right? It's more like a machine, like a vending machine or a jukebox. Okay, we're gonna continue working on problems like this here. But what I want to say is that sometimes you'll be given these problems and we'll have to do operations with the functions and they don't give you equations. What they'll do is they'll say the graphs below represent functions f of x and g of x. And they'll give you two functions. And these functions will have to be pretty well defined. What I mean by that is that I'm going to have to draw these really carefully so that you have all the details that you need to accurately answer these questions. So give me just one moment while I reproduce these graphs. It looks like we have one at -2 and this is 1. I'll label the points here in a second. And then this goes to this point right there. Now we have 1, 2, 3, 1, 2, 3 down. We have an open circle there. And that goes through this point. And it also goes through this point. Okay, I think that should be enough to get this first graph. So something that looks like this and then looks like that. Okay, we're going to say that this is the function f of x. And this other graph looks like 1, 2 up. We have a point there. Then we go over 1, 2, but go up to 4. 1, 2. Like so. Go over to -2 and then up to 4 as well. And then we're just flat on either side. Okay, so it perfectly flat, goes down to this middle point. Boom. Okay, and we're going to call this function g of x. Okay, this is at the point -2, 1. This one is at 0, -2. This one is at 2, 0. This one is at 0, 2. This one's at 2, 4, and this one's at -2, 4. Okay. So take a moment. Let me see if I can zoom in without losing too much of it. Okay. Try to reproduce those graphs. And then we want to find f plus g at -2. We want to find f times g evaluated at 0. And then maybe f divided by g also evaluated at let's say evaluated at 2. And then finally, I'm going to say g divided by f evaluated at 2. So we want to do these 4 problems. Okay, so I want you to think about what has been given to us, right? They gave you 2 graphs which represent 2 functions, function f and function g. You could also call them function f of x or g of x, but because I'm particularly lazy, I like to just say f and g, okay? So we have these 2 functions f and g, and we want to evaluate them at the x value of -2, and then add those outputs or add those 2 y values together, okay? So remember that this is the x value that they've given you. What we need to do is think about taking f of 2, figuring out what that y value is supposed to be, and then adding it to whatever g of 2 is. Okay, remember this is not multiplication. We're taking the input and finding the corresponding output value. So I need to find out what this y value is here. And I need to find out what this y value is so that I can add them together. So what you'll do is you'll go to the graph that we're calling the function f, and that's this graph over here. We'll go to the x value of 2 and then return that y value. So the y value here at this point is 0. Okay, so we have 0 plus whatever g of 2 is. So g, I'll go to this other graph go to the x value of 2, and then return the corresponding y value. And the ordered pair tells me that the y value is 4, but you could also just reference the y-axis and get that that's 4. So what we're really doing when they're asking us this question is just adding 0 plus 4. So that should be 4. Does that make sense, or do we have any questions about that? So even if we're not given equations, we can still do math with these functions so long as we're given either a graph or a table, right? In this kind of problem, it's just going to feel like we're looking up a value so that we can actually do whatever the operation they're asking us to do is. Okay, so now think about what this one's asking you to do. F and G, when they're right next to each other, that's implying multiplication. So really, we need to find F evaluated at the x value of 0, then multiply that by whatever G evaluated at the x value of 0 is. So F of 0, we go to this function here, and we go to the x value of 0, and we go down and touch the graph. The purple part is the graph that we're interested in, and we take the y value here. The y value is -2. So I'm going to take -2. I'm going to multiply it by whatever G evaluated at 0 is. So I'll go to the x value on the second graph, go up to 2, and that's my y value. So I'm multiplying that by 2. And then I'm just multiplying these two numbers together, multiplying the two outputs together. So that should be -4. Okay, so take a minute to try to do the last two. Does anybody have any questions about this one? Okay, I always like to set these up before I actually look up what the y values are. So I always say that, okay, this should just be f evaluated at 2 over g of 2. And then I'll go and find what f of 2 is supposed to be. So if I go over to 2 and I get the y value here, that should be 0. If I go to g of 2, go over 2 and up 4, that's the value of g of 2, 4. But I have this fraction 0 over 4, and that's fine. You know, I could throw that in the calculator and see what it tells me. So if I wanted to reduce this, 0 divided by 4 is just 0. So in this case, my answer would just be 0. Does anybody have any questions about that one? Now you might think that the next question is a little bit more confusing, but if we set it up the order here matters, right? So if G is being divided by F now, then I'm going to put G of 2 on top and F of 2 on the bottom. So you could look up these values again, but you might notice that we already looked up the values using the graphs before. G of 2, if I go to the graph, is just 4, right? That's the corresponding Y value. So here I'm putting 4 on top. And F of 2, if I go over to 2, the Y value here is 0. So that means I'm putting a 0 on the bottom. Can I divide by 0? So we're just going to have to say that this is undefined because you cannot divide by 0. Okay, now there's another flavor of this kind of problem where they give you two different tables and ask you to do the operations. I'm not going to run through an example of that because I think you guys can challenge yourselves to think critically about how to get those. If you have trouble with those, come to Math World and we'll work through those. But we do have one more kind of operation that we can do with functions, and this is one of the neat things about functions that make them super useful. So let's say we are given two functions, as we typically are. One of the functions, f of x, is equal to 9x plus 2. And the other function is g of x, and that's equal to do I want to do something so bold? Let's do something less bold than that. Let's go with 2x squared. Okay. We have one operation that doesn't make any sense when it comes to working with just numbers. And this operation is specific to functions. Okay. Now, this is the analogy that I want you to go with me on, okay? Has anybody seen like a really fancy refrigerator that has a computer monitor, like a touch screen, basically a tablet in the front door of the refrigerator, right? These things are like super expensive, but they do all kinds of things. They're not only keeping your food cold, you can also link up to the internet and do all other kinds of functions, like update your grocery list. You could order your groceries to be delivered to you using Shipt or whatever the delivery service is nowadays, right? But basically what they've done is they've taken a machine, let's call it machine 1, and they've put, let's just call that the computer screen or the tablet, and they've taken machine 2, so this is the computer, and machine 2, which is the fridge, and they have taken that machine and plugged it into a different machine so that you get all kinds of new functionality. What we would call in mathematics, we would call this in mathematics is composition. And you can think about it as plugging one function into another function to make a more complicated function or a more complicated machine. Okay, and that's something that you can't do with numbers. Like I can't plug 2 into 1 or 13 into 14 and get some sort of new number that unless I have some sort of arithmetic operator like addition, subtraction, multiplication, and division. But I can't say like 1, and let me just make this symbol. I'm going to put an open circle here. I take 1, this little open symbol means composed with. And let's say that I took these two things and created a new number, and I'm going to make the symbol look like this. That's not something that we do with numbers. I mean, I guess if you want to invent your own number system and your own language and your own script, then by all means have at it. But we're not going to be doing that with numbers. But this idea of like taking a machine like a computer and plugging it into a fridge to get some more modern, fancy machine, that is an operation that we can do in the real world. And that's something that we can do with these two functions that I've given you here. Okay, because functions take input values. Those input values don't have to be numbers. They could be other functions. So the two functions I gave you were f of x is equal to, and I forgot what they were, 9x plus 2, and g of x, I'm pretty sure I used 2x squared and left it at that. Yeah. Function composition can be written in two ways, and here order does matter. So I can write f, and then this open circle is a new operation symbol. F composed with g of x. Sometimes students will read it as fog. That's fine. However you need to think about it, is telling you to take this function g of x and plug it into the input value of f. So I will write that as f, we're going to open up that machine, and we're going to plug in to that machine g of x. And I know that this looks complicated at first, so just write it down, and I'll explain in due time. I have these two functions. F of x is equal to 9x plus 2, and I have g of x is equal to 2x squared. Imagine that I wanted to open up f, and the input here I'm going to plug in is this function here, g of x. But I'm plugging in 2x squared as the input for this function. That means that if I write the function f of x, which was originally 9 times the input plus 2, if I've plugged in the other function as the input for the first function, then I can plug in 2x squared right here and then simplify that and call it f composed with g. And when I say simplify, I mean I'm going to go ahead and distribute the 9. So I get 18x squared plus 2. This is a new function. This is the refrigerator that has the tablet on the front door. It's a new fancier function. And we're going to call that function f composed with g of x. But the order of composition matters. Because before, my analogy was that we take a tablet and stick it to the inside of the refrigerator, right? But what if we took a refrigerator and then put it into a computer, right? We had like a little refrigeration unit attached to our computer. That would be a different kind of device. So order of composition matters. And let's see what I mean by that. So let's change the order so that we're still working with the same two functions. F of x is equal to 9x plus 2. And g of x is equal to 2x squared. But this time we're going to be asked to find g composed with f of x. And in this case, we're taking the first function now and plugging it into the second function. So you can think about it like we're taking g, we're going to open that up, and the input we're going to plug in is whatever the function f of x is. So in that case, we're taking f of x, which is originally 9x plus 2, as the input. You could think of it like this, as the input that goes there, which is going to replace this x. So now, because the order is changed, this operation is now 2 times some input squared, but that input is the first function 9x plus 2. So now if we want to simplify this novel function that we have to square this polynomial. So I'll have to do 9x plus 2 times 9x plus 2, and then simplify that. So let me go ahead and multiply this out. I have 2, and then that will be 81x squared. I'll have plus 18x plus 18x plus 4. I can combine like terms if I wanted to. So 81x squared plus 36x plus 4. And then finally, I can distribute out the 2. And I would get, have no idea what that is times 2. 81 times 2, 162. I probably should have guessed that. Plus 72x plus 8. And this is the new function that we have that we could call g composed of f of x. And one specific kind of problem that you will see in MyLabs Plus that's related to this is that they will give you 2 tables that represent functions, and you'll have to do this composition operation. So they might give you a table that looks like this. X and then f of x are our values here. So this is our function values. And we have 4 values in the table. We have 9, 12, 10, and 20 as our input values. And then for this particular function, they've given us 10, 18, 49, and 51 as our output values. They've given us another table where they're calling these the input values, and they're saying the output values of this table are g of x. And we're given 4 values here as well, which are 11, 20, 9, and 10 are the input values there. And our output values are 21, 17, 20, and 19. So you could think of this as this table represents the function f, and this one represents the function g, and they're asking us to find g composed of f evaluated at 9. And so we're going to have to think through what this means using the table. Well, I gave you the last examples as equations that we plugged into each other. But the definition of this composition is saying that we're going to take f of 9 and plug it into g. So what I like to do is I write the function g down and I open it up with a big set of brackets because I'm going to plug something in there. The thing that I'm plugging in is f of 9. F evaluated at 9. So I need to work this problem from the inside out. Now that I have f of 9 here, I need to use the table that represents the function f and find the output value or the corresponding y value that goes with this input value of 9. Okay, so what is the y value that I get when I use 9 as the input in the function f?
10.
10?
And
10. 10, right? So I look at this table f, the input is 9, the output is 10. Okay? Does everybody see that? So that means that I'm looking really at g, and I know that this outputs to 10. So now all I'm really looking for is g evaluated at 10. So now what is the output when I use 10 as the input for the function g?
$19.
And that's the answer. So you're using this composition idea to look up a value in one table, plug that value as the input into the other table, and then get the output. Okay. That is all the time we have for now. I know that it wasn't a lot of examples of that problem, but we can talk about it more at the beginning of class next time. Otherwise, come into Math World and we'll talk about it a lot more. I'll see you guys on Wednesday. There's some homeworks in My Labs Plus associated with what we just covered right now. But we're going to get into more in-depth analysis of quadratic equations. So the stuff that we looked at the beginning, where we looked at the graphs of parabolas, we're going to get all into that, just all up in the mix. Okay. So if you're still sort of like having jet lag from test 3, make sure that you're getting the practice that you need. Do not avoid it or put it off, because we only have a couple weeks left until finals. Okay. So let's do this. Let's do it right. And if you need help at all, or if you're nervous or scared, reach out to me, send me a message, and we can set up some meeting, right? Doesn't matter what time of day, what time of night, I am here to support you guys, but you have to reach out, okay? All right, well, you guys enjoy the rest of your day, and I'll see you next time.
Thank
Enjoy
you.
your day.
Thank you.
Thank you.